There is a wall at the edge of the universe. You cannot touch it. You cannot see it. But it is there, surrounding every civilization that has ever existed, and every civilization that ever will, and it is utterly, completely, inescapably indestructible. It is not made of stone. It is not made of metal. It is not made of any substance you could name. It is made of physics itself, the speed of light, 300,000 kilometers per second, 1 billion kilometers per hour, fast enough to circle the Earth 7.5 times in a single second, fast enough to travel from here to the moon in just over 1 second, fast enough to cross the distance between the Earth and the Sun in 8 minutes. And yet, in the context of the universe, impossibly, laughably, heartbreakingly slow. At the speed of light, reaching our nearest stellar neighbor takes 4 years and 2 months. Reaching the center of our own galaxy takes 26,000 years. Reaching the nearest galaxy cluster takes hundreds of millions of years. And the farthest objects we can observe, the ancient galaxies at the very edge of the observable universe, are so remote that even light has been traveling toward us since before the Earth existed, and has still only just arrived. This is the prison we are in, not because we lack the technology, not because we lack the will, but because the universe appears to have been designed, if designed is even the right word, with a speed limit baked into its deepest structure. And that speed limit makes the cosmos effectively inaccessible to any species that plays by the rules. But what if we don't have to play by the rules? What if the speed of light is not a limit on what can move through space, but simply a limit on what can move through space in the ordinary way? What if there are loopholes? What if the universe itself, in its strange quantum mechanical heart, is already breaking its own rules in ways we are only beginning to understand? In the last 30 years, physicists have discovered not one, not two, but several mechanisms, some theoretical, some partially observed, some actively being engineered, that appear to allow information, matter, or the fabric of space-time itself to do something that Einstein's equations call impossible. This is the story of how we are trying to break the universe's speed limit, and why the answer might be stranger, more beautiful, and more terrifying than anyone expected. To understand why faster-than-light travel seems impossible, you have to understand why the speed limit exists in the first place. And to understand that, you have to understand the most counterintuitive idea in the history of physics. In 1905, Albert Einstein published a paper that would remake the world. It was not his most famous paper. It was not about quantum mechanics or the photoelectric effect, for which he would eventually win the Nobel Prize. It was a short, spare document with a title that sounds almost modest. On the electrodynamics of moving bodies. It contained the special theory of relativity. The core idea seems simple. Einstein proposed that the speed of light in a vacuum, what physicists call c, approximately 299,792 kilometers per second, is a universal constant. It is the same for every observer, in every frame of reference, regardless of how fast they are moving. This sounds almost reasonable until you think about what it actually means. If the speed of light must be the same for all observers, then the universe has to do something extraordinary to make that true. It has to make time itself flexible. It has to make the very length of objects flexible. It has to make the very meaning of simultaneous different for different observers. When you move faster, time flows more slowly for you. This is not a metaphor. It is not a figure of speech. It is a measured, verified, experimentally confirmed fact. GPS satellites traveling at orbital velocity experience time passing slightly more slowly than clocks on the ground. The difference is tiny, microseconds per day. But if it were not corrected for, GPS navigation would drift by kilometers within hours. For objects moving close to the speed of light, the effect becomes enormous. From the perspective of a particle accelerated to 99% of light speed, a second stretches into 7 seconds. At 99.9%, a second becomes 22 seconds. At n 99.999%, time slows to a crawl. A single second becomes 700 seconds relative to a stationary observer. And this is where the wall appears. To accelerate any object with mass to the speed of light would require infinite energy. Not a very large amount of energy, not an impractical amount. Infinite, an amount that does not and cannot exist. Because as an object accelerates toward the speed of light, its effective mass, its resistance to further acceleration, increases without bound. The closer you get to light speed, the more energy you need to get closer still. The final meter to the finish line would require more energy than exists in the observable universe. This is why the speed of light is a barrier. Not because of a lack of engineering, not because we haven't built big enough engines, but because the mathematics of space-time itself says that for any object with mass, the speed of light is an asymptotic limit, something you can approach forever but never reach. But here's the thing Einstein did not say, and this is where it gets interesting. He did not say nothing could move faster than light. He said massive objects cannot be accelerated to the speed of light. He said information cannot travel faster than light in the ordinary sense. But the universe, it turns out, is very large. And in its corners, strange things happen that seem, at first glance, to break this rule. The expansion of space itself, for instance, can and does move faster than light. The most distant galaxies we can observe are receding from us at speeds far exceeding the speed of light. Not because they are moving through space at those speeds, but because the space between us and them is expanding faster than light can cross it. Einstein's equations permit this. They always did. It is space that is moving, not matter. This distinction between moving through space and moving with space is the key to everything that follows. The year was 1994. The Berlin Wall had fallen 5 years earlier. The Human Genome Project was underway. The internet was just beginning to connect the world's computers. And in a physics department in Wales, a young Mexican physicist was about to publish a paper that would change the conversation about faster-than-light travel forever. His name was Miguel Alcubierre. His paper was called The Warp Drive, Hyper-Fast Travel Within General Relativity. And what he proposed was not a science fiction engine. It was a mathematical solution to Einstein's field equations, a region of space-time that could carry a spacecraft at any speed, including faster than light, while allowing the passengers inside to feel nothing at all. Let's understand what Alcubierre proposed, because it is genuinely remarkable. The key insight is this: Einstein's equations do not prohibit space itself from moving faster than light. They only prohibit matter from moving through space faster than light. These are different things. And Alcubierre realized that if you could manipulate the geometry of space-time itself, compress it in front of your spacecraft and expand it behind, the region of space containing your ship could move at any velocity you choose. Imagine you are standing on a moving walkway in an airport. You are standing still, not walking, just standing. But you are moving. The walkway is carrying you. Your feet are not moving relative to the walkway beneath them. But relative to the terminal floor, you are traveling at the speed of the walkway. Now imagine a walkway that moves at 10 times the speed of light. You stand still. Space moves. You arrive at your destination having felt no acceleration, no g-forces, no time dilation. From inside the bubble, physics is completely normal. Time passes at its usual rate. You can eat lunch and read a book. Meanwhile, outside, space itself is contracting in front of you and expanding behind you at speeds that violate every common sense notion of what the universe permits. Alcubierre's paper was mathematically rigorous. It was not speculative fiction dressed up in equations. It was a genuine, peer-reviewed solution to Einstein's field equations, a solution that showed, definitively, that the equations of general relativity do not forbid faster-than-light travel in principle. They just make it very, very, very hard in practice. How hard? The original 1994 paper calculated that to create an Alcubierre bubble capable of moving a spacecraft, even a small one, at faster-than-light speeds would require an amount of exotic energy approximately equal to the total mass energy of Jupiter. Not the energy that could be extracted from Jupiter. The entire planet converted to pure energy via E equals mc squared, and then used in a form that has negative energy density. Energy that, in the ordinary universe, is deeply difficult to create and impossible to stockpile. The phrase exotic matter is doing a lot of work here. It refers to matter with negative energy density. Matter that, unlike everything you have ever touched or seen, repels gravity rather than attracting it. It is a theoretical entity permitted by quantum mechanics, but never observed in quantities larger than the subatomic scale. The Casimir effect, a real, measured quantum phenomenon where two metal plates placed extremely close together experience an attractive force due to fluctuations in the quantum vacuum, can produce tiny amounts of negative energy density between the plates, but the amount needed for an Alcubierre drive is not small. Jupiter has a mass of approximately 2 × 10⁻27 kilograms. The total energy equivalent of Jupiter's mass, E equals mc squared, is roughly 1.8 × 10⁴ joules. That is more energy than the Sun will radiate across its entire 10 billion year lifespan. It is approximately equal to the total luminous energy output of the observable universe over 1 second, for a drive the size of a spacecraft. The physics community's initial reaction was a mixture of fascination and despair. Yes, Alcubierre had found a genuine loophole in general relativity. Yes, the loophole was real mathematics, but the energy requirements made it approximately as practical as building a staircase to the moon out of gold. And then, 30 years of physics happened. The first major revision came in 1999, when physicists Chris van den Broek showed that a small modification to the bubble geometry could reduce the energy requirements by an enormous factor, from Jupiter's mass energy to roughly the mass energy of a proton. This was still not easy, but it was not Jupiter. The direction of travel was clear. The energy requirements of the Alcubierre drive were not fixed. They could be optimized. Over the following 2 decades, physicists found ways to reduce the requirements further still. Harold Sonny White at NASA's Johnson Space Center, a name we will return to, spent years working on Alcubierre drive modifications, eventually proposing oscillating bubble geometries that could reduce requirements by multiple additional orders of magnitude. In 2012, White announced that NASA had actually begun low-energy experiments to test these concepts using a device called the White-Jude Warp Field Interferometer, an instrument designed to detect whether a small region of spacetime could be measurably warped by an applied electromagnetic field. The experiments did not produce a warp field. They were not expected to. The energies involved were far too small to create any detectable warping of spacetime. But the experiment represented something important, the movement of warp drive theory from pure mathematical speculation to the first tentative steps of experimental investigation. And then, in 2021, something happened that the physics community had not expected. A team of physicists, led by Harold White, now at the Limitless Space Institute, along with colleagues from the Applied Physics Group, published a paper announcing that they had discovered a new class of warp drive solutions that they called the positive energy warp drive. Unlike Alcubierre's original design, which required exotic matter with negative energy density, these new solutions, discovered through a systematic computer search of the parameter space of warp bubble geometries, were claimed to be achievable using only ordinary positive energy matter. the physics community's response to this paper was intense. Some physicists were skeptical, others were cautiously excited. The paper was real, published in the peer-reviewed journal Classical and Quantum Gravity. The mathematics appeared to be correct, but the implications were enormous. And in physics, enormous implications require careful scrutiny. Eric Lentz at the University of Göttingen, one of the paper's authors, was careful in his framing. The new solutions eliminated the need for exotic matter. They did not eliminate the enormous energy requirements overall. The amounts of energy needed were still far beyond any technology we currently possess. But the barrier of exotic matter, the most fundamental objection to Alcubierre's original proposal, appeared to have been removed. We are not close to building a warp drive. Let's be completely honest about that. We are not close in the way that the Wright brothers in 1900 were not close to building a Saturn V rocket. But we may have moved from "this is mathematically forbidden" to "this is mathematically possible but extraordinarily difficult." And in physics, that is an enormous distance to travel. In 1935, Albert Einstein wrote a paper with Boris Podolsky and Nathan Rosen that was intended to prove that quantum mechanics was incomplete. The paper described a thought experiment. Two particles interact and then fly apart. According to quantum mechanics, their properties remain entangled, mathematically linked, even after they separate. Measure the spin of one particle, and the other particle's spin is instantly determined, regardless of the distance between them. Einstein hated this. He called it spooky action at a distance. He was certain it proved that quantum mechanics was missing something. Some hidden variables that determined the particle's properties all along, so that no genuine instant communication was actually occurring. The particles were, in his view, like a pair of gloves separated into two boxes and shipped to opposite ends of the world. When you open one box and find a left glove, you instantly know the other is a right glove. But no information has been transmitted. The gloves were always determined. For 30 years, this seemed like a philosophical debate that could not be resolved by experiment. Then, in 1964, a Northern Irish physicist named John Stuart Bell published what is now called Bell's theorem, one of the most important results in the history of physics. Bell proved mathematically that if hidden variables existed, if the particle's properties were determined from the beginning, like the gloves, the statistical correlations between measurements of the two particles would obey a specific inequality. If quantum mechanics was right, those correlations would violate the inequality. The two predictions were different, and different predictions can be tested. The experiments were done, first by John Clauser in the 1970s, then more definitively by Alain Aspect in 1982, and then with ever-increasing precision by dozens of teams around the world over the following decades. The results were consistent. Bell's inequalities were violated. Quantum mechanics was right. The correlations were not explainable by hidden variables. This was confirmed decisively in 2022, when the Nobel Prize in Physics was awarded jointly to John Clauser, Alain Aspect, and Anton Zeilinger, three physicists who had spent decades designing and performing experiments to test Bell's theorem. The Nobel Committee's announcement was unambiguous. Quantum entanglement is real. The particles really are instantaneously correlated, regardless of distance. The universe really does have this strange, instantaneous connection built into its fabric. Two particles, once entangled, share a mathematical relationship that updates instantaneously across any distance. When one is measured, the other responds. So, why can't we use this to send messages faster than light? This is the question that everyone asks. It is an obvious question. It is a good question. And the answer is one of the most elegant and frustrating things in all of physics. You cannot use quantum entanglement to send information faster than light because of the no communication theorem. Here is why. When you measure an entangled particle, you get a random result. You cannot choose what result you get. You cannot control whether the particle spins up or spins down. You just measure it and get whatever quantum mechanics gives you. The partner particle, across any distance, instantly collapses into the correlated state. But the partner particle's observer also just gets a random result. They see a random string of ups and downs. You see a random string of ups and downs. Neither string contains any information by itself. It is only when you bring the results together, through a classical channel, at normal light speed or below, that the correlation becomes visible. The entanglement allows you to create perfect correlations, but you cannot control what those correlations say, and therefore, you cannot encode a message. The universe, it seems, was very careful about this. Entanglement is real and instantaneous, but it is also by construction useless for faster-than-light communication. It is as if the universe wrote a rule that says, yes, there is an instantaneous connection between distant particles, but you are not allowed to use it as a telephone. Physicists have tried many approaches to circumvent the no communication theorem. All have failed. The theorem appears to be as robust as any result in physics. As long as quantum mechanics is correct, and it has passed every experimental test anyone has designed, the no communication theorem holds. And yet, and this is where it gets interesting again, entanglement has given us something almost as remarkable: quantum teleportation. Quantum teleportation is not science fiction. It has been demonstrated in laboratories since 1993, when Charles Bennett and colleagues at IBM published the theoretical framework. In 1997, the first experimental demonstration was performed in Innsbruck, Austria, by Anton Zeilinger's group, the same Anton Zeilinger who shared the 2022 Nobel Prize. What quantum teleportation does is this: it takes the complete quantum state of a particle, all the information that defines what that particle is, and transfers it exactly to another particle in a different location. The original particle is destroyed in the process. The copy is perfect. The information arrives at the destination. The remarkable thing is that the quantum state arrives at the destination instantly, in a sense. The entanglement collapses instantaneously. But the two classical bits that Bob needs to complete the teleportation must travel at normal light speed. Without those bits, Bob's particle is in a completely random, useless state. With them, it is a perfect copy of Alice's original. The quantum information teleports. But the classical signal creeps along at light speed or below. No information has been transmitted faster than light. The no communication theorem remains intact. By 2023, quantum teleportation had been demonstrated over distances of over 1,000 kilometers, between a satellite and a ground station, using China's Messias satellite. The fidelity of the teleported state was near perfect. The physics works. None of this gives us faster-than-light communication today. But it opens something. It demonstrates that quantum mechanics contains resources: entanglement, teleportation, non-local correlations that are stranger than classical physics ever allowed for. And it is in the gap between what these resources allow and what they forbid that some physicists believe a real loophole might exist. We will return to that possibility. But first, there is another mechanism, one that is, in some ways, even more radical than anything Alcubierre or Bell imagined. In 1935, the same year Einstein wrote his entanglement paper with Podolsky and Rosen, he published a second paper, this one with his collaborator Nathan Rosen. This paper described what they called the Einstein-Rosen bridge, a solution to general relativity's field equations that connected two distant regions of space-time through a tunnel. It was not, at the time, called a wormhole. That name came later from physicist John Wheeler, who coined it in 1957. But the mathematics was there from the beginning. The equations of general relativity permit the existence of tunnel-like structures connecting distant points in space-time, not as approximations, not as metaphors. As exact solutions to the equations Einstein himself developed. The original Einstein-Rosen bridge had a problem. It was not traversable. The throat of the bridge, the tunnel connecting the two regions, would collapse faster than any signal or traveler could cross it. Even at the speed of light, you would not make it through. The bridge would pinch off and destroy everything inside before the transit was complete. This seemed to close the door. Then, in 1988, two physicists, Kip Thorne and Mike Morris at Caltech, were asked to help the novelist Carl Sagan with a problem. Sagan was writing a science fiction novel called Contact. He wanted a mechanism to allow his protagonist to travel between stars quickly. He had considered black holes, but the physics was wrong. He called Thorne, a man he had known for years. Thorne took the problem seriously. He and Morris spent months working through the mathematics, asking a specific question. What conditions, if any, would allow a wormhole to be traversable, stable enough for a human being to enter, pass through, and emerge on the other side? The answer they found in 1988, published in the American Journal of Physics, was this. A traversable wormhole is mathematically possible in general relativity, but it requires something at its throat, a material whose energy density is less than zero. Exotic matter, again. The negative energy density required to hold a wormhole open is the same class of substance required by the Alcubierre drive. And like the Alcubierre drive, small amounts of it do exist in the laboratory. The Casimir effect between closely spaced metal plates produces measurable negative energy density. The universe, at the quantum level, allows for regions where the energy density drops below zero. But holding a wormhole open requires enormous amounts of it, and concentrating it into the geometry required to create a stable throat is a challenge of a kind no engineering tradition has ever attempted. The wormhole story took an extraordinary turn in 2022, one that made headlines around the world and confused nearly everyone who reported on it. In November of that year, a team of physicists led by Maria Spyropoulou at Caltech published a paper in the journal Nature. They had used Google's Sycamore quantum computer, one of the most powerful quantum computers ever built, to simulate the behavior of a holographic wormhole. The experiment was immediately misrepresented by science journalists as evidence that a real wormhole had been created in a laboratory. This was not what had happened, but what had happened was extraordinary in its own right. The experiment was based on a profound idea in theoretical physics called the ER equals EPR conjecture, proposed in 2013 by Juan Maldacena and Leonard Susskind, two of the most prominent physicists alive. The conjecture proposes that Einstein-Rosen bridges, wormholes, ER in Maldacena and Susskind's notation, and Einstein-Podolsky-Rosen pairs, entangled particles, EPR, are, in some deep sense, the same thing. That quantum entanglement and wormhole connectivity are two descriptions of a single underlying phenomenon. If ER equals EPR is correct, and it is currently one of the most actively researched ideas in theoretical physics, then every pair of entangled particles is connected by a microscopic wormhole. The spooky action at a distance that Einstein hated is not action at a distance at all. It is information traveling through a wormhole, a tiny subatomic tunnel that connects the two particles. This does not immediately give us a way to travel faster than light. The wormholes in question are subatomic in scale and not traversable by any macroscopic object. But the implication is breathtaking. The fabric of space-time and the quantum mechanical structure of matter may be, at the deepest level, the same thing. Wormholes are not exotic objects added to a universe that otherwise lacks them. They are built into the structure of quantum mechanics itself. The 2022 experiment on Google's quantum computer simulated a 9-qubit system described by a specific theoretical model, a two-dimensional holographic theory with a gravitational dual, and showed that a signal injected on one side of the simulated system appeared with appropriate quantum teleportation characteristics on the other side. The researchers described this as the signal traversing a holographic wormhole. Whether this constitutes a genuine wormhole traversal, even in a simulated sense, remains debated. Theoretical physicist Matt Strassler wrote a careful analysis arguing that the experiment had not demonstrated anything fundamentally new about wormhole physics, only about quantum teleportation. Other physicists, including members of the experimental team, maintained that the wormhole interpretation was meaningful. What is not debated is this: the experiment was real, the data was real, and the theoretical framework that connects quantum entanglement to wormhole geometry, while still unproven in the strongest sense, is taken seriously by some of the best physicists in the world. One of the strangest predictions of quantum mechanics is that empty space is not empty. The quantum vacuum, the lowest energy state of space-time, is filled with what physicists call virtual particle pairs. These are not hypothetical. They are not artifacts of the equations. They are real, measurable phenomena. Particles and their antiparticles that blink in and out of existence on time scale so short that they cannot be directly observed, but whose effects can be measured precisely. The Casimir effect, predicted by Dutch physicist Hendrik Casimir in 1948 and first experimentally measured by Marcus Sparnay in 1958, arises directly from these vacuum fluctuations. Place two conducting plates very close together, close enough that the wavelengths of many virtual particles are too long to fit between them, and the vacuum fluctuation pressure inside the gap is lower than outside. The plates are pushed together. The force is tiny. For plates separated by a micrometer, the pressure is about 1 atmosphere. For plates separated by 10 nanometers, the pressure rises dramatically. The force is real. It has been measured. It represents negative energy density, a region of space where the energy is genuinely, measurably below the zero-point vacuum energy of ordinary space. Researchers have been exploring whether Casimir cavities, carefully engineered arrays of plates and geometries, could produce negative energy densities in larger amounts. The physics group at Applied Physics in New York, the same group that included Harold White and published the 2021 Positive Energy Warp Drive paper, has also published work on Casimir energy harvesting and on the theoretical potential of Casimir effects for engineering negative energy density. The amounts involved are microscopic. We are talking about femtojoules, tiny fractions of a joule, not the Jupiter mass energy the Alcubierre drive originally required, but the direction is consistent. The universe does produce negative energy density through quantum effects. Engineers with precise enough control over nanometer scale geometries can, in principle, design structures that maximize these effects. Whether that path could ever lead to a warp drive or a traversable wormhole remains deeply uncertain. The gap between femtojoules and planetary mass energies is not a gap that any roadmap currently bridges, but it is a gap that was once infinite, because negative energy density was once thought not to exist at all, and now it demonstrably does. In 1962, a Columbia University physicist named Gerald Feinberg began thinking about the implications of special relativity for hypothetical particles moving faster than light. The math was interesting. For an ordinary massive particle, the Lorentz factor, the term in Einstein's equations that governs time dilation and mass increase, goes to infinity as velocity approaches the speed of light. This is why ordinary particles cannot reach light speed. The energy required becomes infinite. But Feinberg noticed something. If a particle started out on the other side of the light barrier, If it had always been moving faster than light from the moment of its creation, a different version of the Lorentz factor applied. Instead of producing infinite values at light speed, it produced imaginary numbers, the square root of -1, mathematically. The energy of such a particle would be imaginary. Feinberg named these hypothetical particles tachyons, from the Greek word for swift. They had an unusual property. Unlike normal particles, they would lose energy as they slowed down toward light speed. To bring a tachyon to a halt would require infinite energy, the same barrier that prevents ordinary particles from reaching light speed, but inverted. A tachyon is permanently trapped above the light barrier the same way ordinary matter is permanently trapped below it. In 1967, Feinberg published a paper arguing that tachyons might be real particles that quantum field theory could accommodate. The physics community was intrigued but skeptical. Searches for tachyons have been conducted since the 1960s. None have been found. No experimental evidence for freely propagating faster-than-light particles has ever been confirmed. In 2011, researchers at the Opera experiment in Italy briefly announced results suggesting that neutrinos, tiny, nearly massless particles that travel close to the speed of light, had arrived at a detector 60 nanoseconds. Faster than light speed would have permitted. The result was later traced to a faulty fiber optic connection and a loose cable. The neutrinos had not broken the speed limit. Tachyons, as free particles, appear not to exist in nature, but the word has not disappeared from physics. In quantum field theory, a tachyonic field is a field whose particle has imaginary mass, not because it moves faster than light, but because it represents an unstable equilibrium. The Higgs field, before it settled into its current state after the Big Bang, was tachyonic in this technical sense. This does not mean the Higgs boson travels faster than light. It means the field was in an unstable configuration that spontaneously broke symmetry to reach its current stable state. Tachyons, in this sense, are not travelers. They are mathematical signatures of phase transitions, moments when a field changes its ground state. They tell us about the universe's history, not about faster-than-light communication. As a means of FTL travel, tachyons remain theoretical, probably do not exist as free particles, and even if they did, it is not clear they could be controlled or used for communication in a way that preserved causality. In 2013, two theoretical physicists, Juan Maldacena at the Institute for Advanced Study in Princeton and Leonard Susskind at Stanford University, published a short, dense paper with a deceptively simple title, Cool Horizons for Entangled Black Holes. The paper proposed something radical. It suggested that Einstein's two great contributions to non-locality, the Einstein-Rosen bridge, wormholes, and the Einstein-Podolsky-Rosen thought experiment, entanglement, were not just related. They were the same phenomenon, viewed from different mathematical perspectives. Every pair of entangled particles, Maldacena and Susskind proposed, is connected by a microscopic wormhole, not a metaphorical wormhole, not an analogy, an actual Einstein-Rosen bridge, too small to be traversed by any known particle, but geometrically real as a feature of spacetime. The implications of this proposal, if correct, are staggering. First, the fabric of spacetime is not a fundamental substance. It is built from entanglement. The smooth geometry of space that we experience at large scales, the arena in which gravity operates, in which planets orbit, in which light travels, emerges from the quantum entanglement structure of underlying degrees of freedom. Space itself is made of wormholes. Second, entanglement and geometry are the same language, spoken at different scales. When physicists study quantum entanglement using quantum information theory, and when they study wormhole geometry using general relativity, they are studying the same physics from two different mathematical angles. Third, This provides a possible route toward reconciling quantum mechanics and general relativity, the two great theories of physics that have resisted unification for nearly a century. If space-time geometry emerges from entanglement, then perhaps the equations of general relativity emerge from quantum mechanics, and not the other way around. The ER equals EPR conjecture is not proven. It is not a theorem. It is, at this point, a proposal with supporting evidence from specific theoretical models, particularly the ADS/CFT correspondence, a precise mathematical duality between a gravitational theory in a particular curved spacetime and a quantum field theory on its boundary. Within this model, the ER equals EPR relationship holds exactly. Whether it holds in the real universe, in flat spacetime, for electrons and protons and the particles that make up ordinary matter, is not known. The theoretical machinery for proving it in the general case does not yet exist, but the evidence from the ADS/CFT context is striking, and the theoretical community has taken it seriously enough that ER equals EPR is now central to several of the most active research programs in fundamental physics, including the firewall paradox, black hole information, and the holographic principle. What does this have to do with faster-than-light travel? Directly? Not much. The wormholes implied by ER equals EPR are Planck-scale structures, not traversable tunnels. They connect particles, not spacecraft. And even if they could be enlarged, a question that is not yet well posed, the no communication theorem would appear to prevent information from traveling through them faster than light, but indirectly, perhaps everything. If space-time is made of entanglement, then the structure of space itself, the distances between objects, the very topology of the cosmos, is not fixed. It is a property of the entanglement network. Change the entanglement, and you change the geometry. In principle, a sufficiently advanced technology that could manipulate entanglement at large scales would be manipulating space-time geometry. This is not warp drive engineering. It is something deeper, entanglement engineering, rewriting the quantum network from which space itself is built. We have no idea how to do this. We do not know if it is possible at all in the general case, outside the specific mathematical models where it has been shown to work. But the theoretical possibility exists, and theoretical possibility in the history of physics has a way of becoming technological reality, over time scales that are usually longer than anyone hopes and shorter than anyone fears. We have traveled a long way through the physics. Let's take a moment to ask a question that doesn't get asked often enough. What would it actually mean to travel faster than light? Not the engineering, not the energy requirements, the human meaning of it. Human history is, on the largest scale, the story of travel becoming faster. We walked, then we rode animals, then we built ships, then trains, then automobiles, then aircraft, then spacecraft. Each acceleration in travel speed opened up a larger world, new continents, new peoples, new resources, new ideas. The radius of the human world expanded, and in that expansion, civilization grew. The radius of our reachable world is now approximately the diameter of the solar system. Voyager 1, launched in 1977, is the farthest human-made object from Earth. It is roughly 24 billion kilometers away, about 160 times the distance from the Earth to the Sun. It is moving at approximately 17 kilometers per second. At that speed, it would take Voyager approximately 75,000 years to reach Proxima Centauri. This is the ceiling of human civilization's current reach. Not because we lack the will, not because we lack the curiosity, but because the distances are simply, staggeringly, incomprehensibly vast. Faster than light travel would not just expand the radius of the human world, it would make the entire galaxy accessible. All 400 billion stars, every planet orbiting them, every biosphere that might exist, every chemical process, every geological formation, every possible variation on the conditions that produced us. A galaxy-wide civilization, not in the far future, but potentially within the time scales that human institutions can plan for. And beyond our galaxy, the local group, Andromeda, 2.5 million light-years away, on a collision course with the Milky Way that will conclude in about 4.5 billion years. The Triangulum Galaxy, the Magellanic Clouds, and beyond, the Virgo Supercluster, 100 million light-years across, the Laniakea Supercluster, 500 million light-years in diameter. The observable universe contains approximately 2 trillion galaxies, each containing hundreds of billions of stars, each star potentially hosting worlds. Without faster-than-light travel, all of this is, for practical purposes, unreachable. The universe is vast. Life is short. Even if we built generation ships, spacecraft where the original crew died and their descendants continued, the number of destinations accessible within 1,000 generations of travel time is vanishingly small. With faster-than-light travel, the universe opens. This is why the problem matters. This is why physicists continue to work on it, even when the obstacles seem insurmountable. Not because they are dreamers ignoring reality, but because the potential reward is the entire universe. And that is a prize worth chasing through any amount of mathematical difficulty. Let's be honest about where we are. We do not have a working faster-than-light drive. We do not have a traversable wormhole. We do not have any confirmed mechanism for superluminal communication. What we have is something more subtle, and in some ways more remarkable. A collection of mathematical structures within our best physical theories that suggest the prohibition against faster-than-light travel is not absolute. Alcubierre's warp drive is a genuine solution to general relativity's field equations. The energy requirements are enormous, but they have been reduced by orders of magnitude through subsequent research, and a 2021 paper claimed to find solutions not requiring exotic matter. The warp drive is not forbidden. It is extraordinarily difficult. Einstein-Rosen bridges, wormholes, are also genuine solutions to general relativity. Traversable wormholes require exotic matter with negative energy density, which exists in small amounts in the Casimir effect. The theoretical barrier has not collapsed, but it has developed cracks. Quantum entanglement is real, confirmed by decades of experiments and the 2022 Nobel Prize. It does not permit faster-than-light communication as currently understood. But the ER equals EPR conjecture suggests it is connected to wormhole geometry in a way that is still being worked out. What physics is telling us is this: the universe is stranger than classical intuition suggests. The ban on faster-than-light travel is real within the framework of special relativity for ordinary matter moving through ordinary space. But the universe contains mechanisms, the expansion of space, quantum entanglement, wormhole geometry, exotic matter, that suggests the deeper picture is more complicated. What physics is not telling us is that faster-than-light travel is easy or imminent or solved. What we are witnessing right now, in the first decades of the 21st century, is the early phase of a scientific confrontation with one of the deepest questions physics has ever faced. We are the generation that proved entanglement is real. We are the generation that detected gravitational waves, ripples in space-time itself, predicted by Einstein's equations, confirmed a century later by instruments of extraordinary precision. We are the generation that photographed a black hole, and then photographed its magnetic field structure, and then watched matter fall into it in real time. We are not the generation that will build the first warp drive. Probably. But we might be the generation that proves it is possible in principle, and in physics and engineering, in the history of human capability. Proving something is possible in principle is often the hardest step. The speed of light is, for now, our wall. It surrounds us. It defines the accessible boundaries of everything we have ever known. But walls, in physics as in history, have a way of falling when the right combination of understanding and will is brought to bear. The equations of general relativity themselves predict mechanisms that could, in principle, allow us to move faster than light. The quantum mechanical fabric of the universe is woven from entanglement that connects distant points instantaneously. The universe has not, as far as we can tell, forbidden faster than light travel outright. It has made it harder than anything we have ever attempted. It has required resources we do not yet have and understanding we have not yet reached. But it has left the door ajar. Harold Sonny White joined NASA in 2000 as an aerospace engineer. By the time he began serious work on warp drive physics in the late 2000s, he had already spent years working on advanced propulsion concepts, ion drives, plasma propulsion, systems designed to push spacecraft faster than chemical rockets could manage, but still well within the conventional speed regime. His turn toward warp drive physics was not, by his account, a turn toward science fiction. It was a turn toward the mathematics of general relativity, and toward a specific question. The Alcubierre metric was a valid solution to Einstein's equations, and the energy requirements had been dramatically reduced by Van den Broek's modification. What would it take to reduce them further? How far could optimization go? White's key contribution was a modification to the shape of the warp bubble itself. Rather than a static shell of exotic matter surrounding the spacecraft, he proposed a bubble that oscillated, changing its shape dynamically, like a soap bubble vibrating, rather than maintaining a fixed geometry. His calculations suggested this oscillation could reduce the exotic matter requirements from a mass energy equivalent to Jupiter all the way down to a mass comparable to a small spacecraft, perhaps 800 kilograms. This was a dramatic reduction. Critics pointed out that the mathematics was more complex than it appeared, and that subsequent analysis by other groups had not confirmed the full reduction. But the general principle that optimization of bubble geometry could significantly reduce energy requirements was broadly accepted. In 2012, White presented his work at a NASA symposium and announced that the team had built the White-Jude Warp Field Interferometer. The device uses laser interferometry, the same basic technique used by the LIGO gravitational wave detector, scaled down to a tabletop apparatus, to search for measurable distortions of spacetime created by a ring-shaped electromagnetic toroid. The expected signal was tiny, far smaller than any gravitational wave. The toroid, operating at energies accessible in a laboratory, could not be expected to warp spacetime by any significant amount. The question the experiment was asking was, can we measure any warping at all? Is the theoretical connection between electromagnetic energy configurations and spacetime geometry something that shows up even infinitesimally in a laboratory measurement? The results of these experiments were never published in a major peer-reviewed journal. White left NASA in 2016 to join the Limitless Space Institute, where he continued working on warp drive adjacent problems. The experiments, as far as public information reveals, did not detect any significant space-time distortion. This is not surprising, and it is not a failure in the sense that a bridge collapsing is a failure. It is rather an acknowledgement that we are at the very beginning of experimental engagement with an effect that would require technology's orders of magnitude more powerful to demonstrate unambiguously. The importance of White's work at NASA was not the experimental result. It was the institutional recognition that warp drive physics deserved serious, funded investigation by people with engineering credentials and access to real equipment. That recognition, however modest its practical output, moved the field from pure academic theory toward the beginning of experimental physics. The Limitless Space Institute, founded in 2019 by Cam Ghaffarian with an explicit mission to advance the scientific and engineering foundations of interstellar travel, has continued this work. The institute funds research into propulsion, physics, astrophysics, and, specifically, the theoretical and experimental foundations of warp drive mechanics. In 2021, the Applied Physics Group, an independent research organization distinct from the Limitless Space Institute but collaborating with it, published the paper claiming positive energy warp drive solutions. This paper, by Alexei Bobrick and Gianni Martir, received significant media attention and was covered by outlets from Popular Mechanics to the New York Times. Bobrick and Martir's approach was systematic in a way that previous warp drive work had not been. Rather than proposing a specific drive and calculating its properties, they surveyed the entire mathematical space of warp drive solutions, using a framework that classified warp geometries by their energy distribution and stability properties, and searched for solutions that met specific practical criteria. Their most striking finding was the class of solutions they called subluminal warp drives with positive energy. These were not faster-than-light drives. They were warp drives, spacecraft surrounded by a bubble of warped space-time, but moving at speeds below light speed and requiring only ordinary positive energy matter to create the bubble. This was significant. Previous warp drive solutions required exotic matter regardless of whether they were faster than light or not. Bobrick and Martir's solutions showed that the exotic matter requirement was not intrinsic to warp drive geometry. It was a feature of specific superluminal solutions. Below light speed, you could in principle warp space-time without breaking any known physical law. The energy required for these subluminal solutions is still enormous by current engineering standards. But it is not exotic. It is not forbidden. It is a matter of scale, not principle. The superluminal solutions in Bobrick and Martir's framework still require either exotic matter or careful fine-tuning of energy distributions that, upon more rigorous analysis, some subsequent researchers have argued, still requires effective exotic matter behavior, even if the total integrated energy is positive. The debate continues. The papers continue to appear. The community continues to refine its understanding. Let's imagine for a moment that the problem was solved, that the exotic matter question had been resolved, that a stable, traversable wormhole had been constructed, that a spacecraft was approaching its entrance. What would the physics of the journey look like? As the spacecraft approached the wormhole's mouth, the crew would first notice the light. Wormholes, if they existed, would be gravitational lenses of extraordinary power. Light from behind the wormhole, from the destination end, would be bent through the throat and appear around the mouth, creating a visual distortion like an enormous lens. Stars visible through the wormhole would be the stars of a completely different region of space. The tidal forces near the mouth would depend entirely on how the wormhole was constructed. The Morris-Thorne solutions allow for arbitrary throat radii, a wormhole with a throat a kilometer wide, held open by exotic matter, could have tidal forces small enough to be entirely survivable. The spacecraft would approach, cross the throat, a transit that might take minutes or hours depending on the length of the connecting tunnel, and emerge on the other side. What would be strangest is what the instruments would show. During the crossing, the crew would be in a region of space-time with significant curvature. Clocks inside the spacecraft would tick at rates slightly different from clocks on each side of the connection. The direction down, toward the nearest gravitational mass, would shift as the spacecraft moved from one gravitational environment to another. Exiting the wormhole on the far side, the crew would find themselves in a completely different region of the universe. The sun would be invisible. The familiar stars would be gone. In their place, the stars of whatever region the wormhole connected to. If the other end was in the Andromeda galaxy, the crew would see Andromeda's stars, its nebulae, its black holes, from the inside for the first time in human history. The journey that would have taken 2.5 million years at light speed would have taken hours or minutes. Depending on the length of the wormhole's interior, Time, relative to the Earth left behind, might have passed at the normal rate. The crew would return through the wormhole, if two-way transit were possible, and be the same age as when they left. This depends on the specific wormhole geometry. Some solutions connect regions not just in space, but in time, potentially allowing travel backward in time as well as forward. This is the time travel paradox problem, one of the most serious theoretical objections to traversable wormholes, and a subject of ongoing research. Hawking himself proposed in 1992 a chronology protection conjecture, the idea that the laws of physics conspire to prevent the creation of time machines, even when the equations of general relativity appear to permit them. Quantum effects near any wormhole that could be used for time travel would, he argued, build up into a destructive burst of radiation that would destroy the wormhole before it could be used. The conjecture is not proven. It is an argument based on physical intuition applied to calculations in quantum field theory and curved space-time, a regime where our theoretical tools become uncertain. Some subsequent work has supported Hawking's argument. Some has challenged it. The question of whether traversable wormholes would inevitably lead to time travel paradoxes, and whether those paradoxes would destabilize any attempt to create them, is unresolved. It is, however, a question that can be asked precisely and investigated mathematically, which means it is a scientific question rather than a philosophical speculation. The 2022 Google wormhole experiment, the one that generated extraordinary press coverage and equally extraordinary confusion, deserves a more careful treatment than it typically receives. Because buried in the controversy is something genuinely new, the experiment used Google's Sycamore quantum processor, a device containing 53 superconducting qubits, quantum bits, cooled to temperatures colder than outer space. The research team used 9 of these qubits to implement a specific theoretical model, the Sachdev-Ye-Kitaev model, abbreviated SYK, a system of fermions with random all-to-all interactions that has a special property known to physicists as holographic duality. Holographic duality, also called ADS/CFT correspondence, is one of the most powerful tools in modern theoretical physics. It states that certain quantum theories defined on a boundary of a space are exactly equivalent to gravitational theories in the interior of that space. A quantum system on a two-dimensional surface is dual to a gravitational system in a three-dimensional interior. The SYK model, it turns out, has a gravitational dual that includes wormhole solutions. When two entangled SYK systems are coupled together, the gravitational dual description is two black holes in the higher dimensional space connected by an Einstein-Rosen bridge, a wormhole. This is not metaphor. Within the ADS/CFT framework, it is an exact mathematical equivalence. What the Google experiment did was this. They prepared two 9-qubit SYK systems in an entangled state corresponding, in the gravitational dual, to two black holes connected by a wormhole. They then injected a signal into one system, let it evolve, and observed whether the signal appeared in the other system in a way consistent with having traveled through the wormhole in the gravitational description. The result? Yes. The signal appeared in the second system in a way that was consistent with the gravitational prediction for wormhole traversal. The quantum computer had simulated, within a specific theoretical model, a wormhole allowing information to pass from one end to the other. Now, the crucial caveat. This was a simulation of a wormhole in a dual description, not a wormhole in our physical space. The 9 qubits on the quantum processor are not physically located at opposite ends of a wormhole in real space-time. They are 9 quantum bits in a refrigerator in California. The wormhole exists only in the mathematical description. In the gravitational theory that is dual to the quantum theory being simulated. but this is precisely where the philosophical interest lies. The ER equals EPR conjecture says that the mathematical equivalence between the quantum description and the gravitational description is not just a mathematical convenience. It is pointing at something real. The entangled qubits and the wormhole in the dual description are, in some deep sense, the same physical object. If ER equals EPR is correct, then the Google experiment was not just a simulation of a wormhole. It was a wormhole, a real Einstein-Rosen bridge connecting the two sets of qubits, just a Planck-scale, non-traversable one. And the traversal of information through the wormhole was real traversal, just not in the macroscopic space we inhabit. This is the leading edge of physics in 2024. Not solved, not certain, but real questions being asked with real experiments by real physicists using real quantum computers. The era of armchair speculation about wormholes is giving way, slowly, incompletely, but definitively, to the era of experimental investigation. It is easy, from within a particular century of scientific understanding, to believe that the major questions are settled. Every century before us has made this mistake. At the end of the 19th century, the physicist Lord Kelvin is often quoted, probably apocryphally, but the sentiment was real, as having said that physics was essentially complete, with only two small clouds remaining on the horizon. Those two clouds were the null result of the Michelson-Morley experiment and the problem of black body radiation. They became special relativity and quantum mechanics. They remade the world. At the end of the 20th century, the standard model of particle physics was complete. Gravity was described by general relativity. The universe was, in principle, understood from its smallest quantum components to its largest cosmological structures. And then the universe surprised us again. In 1998, two independent teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rass, announced that the expansion of the universe was accelerating. Not slowing, as gravity predicted, speeding up. Something was pushing the universe apart. Something that made up approximately 68% of the total energy content of the cosmos. Something that was not matter, not radiation, not anything the standard model described. They called it dark energy. Perlmutter, Schmidt, and Rees received the 2011 Nobel Prize in Physics for this discovery. We do not know what dark energy is. The best candidate, the cosmological constant, a constant energy density of empty space, has a measured value that differs from the theoretical prediction of quantum field theory by approximately 120 orders of magnitude. This is the largest discrepancy between theory and observation in the history of physics. Dark matter, the additional gravitational mass that holds galaxies together, that bends light in ways ordinary matter cannot explain, that makes up 27% of the universe's energy content, has been confirmed by dozens of independent lines of evidence. We have never detected a dark matter particle in a laboratory. We do not know what it is. 95% of the universe, by energy content, is made of things we do not understand and cannot directly observe. The standard model, our most successful physical theory, describes the 5% we can see. This is not a statement of failure. It is a statement of how much physics remains to be done. And here is the implication for faster than light travel. We do not know what dark energy is. We do not know what dark matter is. We do not know whether either of them has properties we have not yet discovered, that could interact with the mechanisms we have been discussing in this film. Exotic matter with negative energy density is required for the Alcubierre drive and for traversable wormholes. We have not found it in useful quantities, but we have discovered that 95% of the universe is made of things we do not understand. The possibility that among those unknown substances lies something with exotic energy properties, something that could, in principle, be harnessed for the physics of warp drives or wormholes, is not outlandish. Dark energy, in fact, behaves at cosmological scales, somewhat like the exotic matter that negative energy density describes at local scales. The cosmological constant represents a vacuum energy with negative pressure, a substance that, in the equation of state of the universe, acts to expand space rather than contract it. This is not the same as exotic matter in the Alcubierre sense, but the family resemblance is there. Physicists who study dark energy and physicists who study warp drives do not yet have a shared theoretical language in which to compare notes. The scales are different, cosmological versus local. The physics may be entirely different, but the possibility that they are connected, that the mysterious accelerating expansion of the cosmos and the exotic energy required for faster-than-light travel are different manifestations of the same underlying physics, has not been ruled out. In the very distant future, tens of billions of years from now, the expansion of the universe driven by dark energy will have separated all galaxies from each other. The local group, the Milky Way, Andromeda, and their satellite galaxies will be gravitationally bound together, an island in an otherwise empty universe. Beyond the local group, every other galaxy will have receded beyond the cosmological horizon. Even light from those galaxies, traveling toward us now, will never reach us. In that future, a civilization without faster-than-light travel would be trapped in the local group forever. The rest of the universe would be permanently inaccessible, not because they lack technology, but because the expansion of space would have moved the destinations beyond any possible reach. This is the long-term horizon of the faster-than-light problem. Not the next century, but the next trillion years. The question of whether the universe is accessible to life or forever fragmented and isolated. The answer depends on physics we have not yet learned. The search for faster-than-light physics is not confined to thought experiments and theoretical papers. There are people working on it right now. At the Limitless Space Institute in Houston, a team funded by private philanthropy is developing the theoretical and experimental foundations for propulsion physics beyond chemical rockets, including the warp drive research program that Harold White began at NASA. At the University of Göttingen, Eric Lentz has continued developing his soliton-based warp drive solutions, a class of warp geometries that use configurations of ordinary positive energy fields to create theoretically a region of moving, warped space-time. At the Applied Physics Group in New York, Bobrick and Martyre's work on the classification of warp drive solutions has continued, exploring the boundary conditions between physically realizable and physically forbidden geometries. At Caltech, Maria Spyropoulou's group, the team behind the 2022 quantum wormhole experiment, continues to develop quantum simulation techniques for exploring holographic physics. Their next-generation experiments, using larger quantum computers, aim to test predictions of the ER equals EPR conjecture with higher fidelity. At CERN, precision measurements of quantum vacuum effects, the Casimir effect, vacuum polarization, photon-photon scattering, continue to probe the properties of empty space at energies and length scales where the difference between possible and impossible might reside. None of these programs has announced a breakthrough. None has produced a prototype. The distance between where we are and where we need to be remains honestly vast, but the direction is consistent. The equations do not forbid it. The universe has, in the last century, surprised us with relativity, quantum mechanics, dark energy, gravitational waves, and quantum entanglement. It has a history of revealing that what we thought were absolute limits were in fact limits of our understanding. The people working on these problems are not dreamers detached from reality. They are physicists who have been trained in the most rigorous intellectual tradition our civilization has produced. They are choosing to spend their careers on the hardest problem in propulsion physics because the potential reward, the opening of the universe, justifies the difficulty. And because, in the mathematics of the universe, the door is not closed. It is just very, very, very hard to open. Miguel Alcubierre was born in Mexico City in 1964. He studied physics at the Universidad Nacional Autónoma de México and completed his PhD at the University of Wales, Cardiff, in 1994, the same year his most famous paper appeared. He had been studying numerical relativity, the use of computers to simulate solutions to Einstein's equations, particularly the dynamics of black hole mergers that would later be detected as gravitational waves by LIGO. The warp drive paper was not his main research. It was, by his own account, a thought experiment he had been turning over in his mind since he was a teenager watching science fiction films. He had grown up with Star Wars and Star Trek. He had grown up with the idea that humanity would one day reach the stars. And as he became a professional physicist, as he learned the full weight of the evidence for the speed limit, he found he was not satisfied with simply accepting the prison. He started with a question: is the Lorentz invariance, the symmetry that makes the speed of light a universal constant, truly absolute, or does it only apply to certain kinds of motion? The answer, as he worked through the equations, was the latter. The Lorentz symmetry that limits particles moving through space does not apply to the space itself. General relativity's equations describe space-time as a dynamic entity, something that can stretch, compress, curve, and, crucially, move, and the motion of space-time is not subject to the Lorentz limit. Alcubierre wrote down a metric, a mathematical description of space-time geometry, that captured what he wanted: a bubble of flat space-time surrounded by a region where space was contracting in front and expanding behind. He showed that the equations of general relativity were satisfied everywhere. He calculated the energy conditions and found that exotic matter was required. He submitted the paper. The response, when it came, was a mixture of fascination and skepticism. Matt Visser, at Washington University in St. Louis, published a detailed analysis arguing that the energy conditions required were even more severe than Alcubierre had calculated. Sergei Krasnikov published a different analysis arguing that the creation of the warp bubble could not be initiated from inside the bubble. A crew could not turn on their own warp drive because the causality structure of the space-time prevented signals from reaching the bubble wall from the interior. Krasnikov's own paper proposed an alternative, a Krasnikov tube, a tube of modified space-time connecting 2 points created by a one-way journey at ordinary speeds and then usable for faster-than-light return trips. The physics of Krasnikov tubes turned out to have their own exotic matter requirements and causality problems. Every attempt to circumvent the problems found new problems. Every proposed solution required deeper understanding of quantum gravity, the still unfinished synthesis of quantum mechanics and general relativity. Alcubierre himself, in interviews over the subsequent decades, has been consistently honest about the challenges. He has not walked back the paper. The mathematics is correct. The solution is a valid solution to Einstein's equations. But he has consistently emphasized that the gap between a valid mathematical solution and a buildable engineering system is enormous, and that the exotic matter problem, in particular, remains the central obstacle. Today, Miguel Alcubierre's 1994 paper has been cited more than 2,000 times in the peer-reviewed physics literature. It has inspired a generation of physicists to work on the theoretical foundations of faster-than-light travel. It has been the starting point for the positive energy warp drive solutions, the soliton warp drives, the Krasnikov tube, and dozens of other theoretical structures that have refined our understanding of what general relativity permits. He did not solve the problem. He showed that the problem was solvable in principle within the mathematical framework of the physics we already had. And in the history of great scientific questions, That is often the most important step. The most serious objection to traversable wormholes is not the exotic matter requirement. It is what wormholes might do to the structure of time itself. General relativity, applied to a traversable wormhole, allows for something called a closed time-like curve, a path through space-time that loops back on itself. A traveler on such a path would eventually return to their own past. They would meet their younger self. They would be able to, in principle, kill their own grandfather, creating a paradox that has no resolution within classical physics. This is not science fiction speculation. It is a mathematical consequence of general relativistic wormhole solutions, first worked out rigorously by Morris, Thorne, and Yurtsever in a 1988 paper titled Wormholes, Time Machines, and the Weak Energy Condition. They showed that a traversable wormhole with one mouth, accelerated to high velocity relative to the other, could, given sufficient proper time, produce a closed time-like curve. The physics community's response was divided. One school, championed most prominently by Stephen Hawking, argued that nature must have some mechanism that prevents closed time-like curves from forming, even if classical general relativity permits them. Quantum effects, he argued, would always build up near any nascent closed time-like curve and destroy the structure before the loop could be completed. He proposed this as a conjecture, the chronology protection conjecture, while acknowledging it was not proven. Another school, including physicists like Kip Thorne, who had helped discover the problem in the first place, argued that the chronology protection conjecture might be wrong, or might apply in some contexts but not others. They pointed out that the quantum calculations near a closed time-like curve are performed in a regime where quantum gravity is needed, where our current equations break down. The conjecture might be right, but we do not yet have the physics to confirm it. A third school, drawing on the work of physicists including David Deutsch, proposed that closed time-like curves might be possible, but that quantum mechanics would prevent any actual paradoxes from occurring. Deutsch showed in a 1991 paper that a quantum system traveling through a closed time-like curve could reach a self-consistent quantum state, a state in which the quantum probabilities were consistent, going backward and forward through the loop. No paradox, but strange consequences for information and causality. Subsequent work by Seth Lloyd and colleagues showed that Deutsch's model produced consequences so strange, including the ability to solve computational problems that are believed to be intractable, that many physicists consider them evidence against, rather than in favor of, the physical realizability of closed time-like curves. The debate is unresolved. The chronology protection conjecture is plausible but unproven. The quantum gravity regime where the answer lies is inaccessible to current theory. And the wormhole time machine problem sits, unresolved, at the intersection of our two greatest physical theories, general relativity and quantum mechanics, where they disagree most sharply. This is the frontier, not the comfortable frontier of problems we know how to approach. The hard frontier, where our best tools produce contradictory answers, where the physics we have is insufficient for the questions we are asking, and where the answer requires something new. That is precisely where the most important discoveries wait. Here is a question that does not get asked often enough. Why is the speed of light the value it is? Why is it 300,000 kilometers per second rather than 3 million or 300 or some other number? The speed of light is not a law in the sense that a mathematical theorem is a law. It is a measured constant, a fact about the universe, not a logical necessity. Some deeper theory might explain why it has the value it has. We do not currently have such a theory. In 1983, the International Bureau of Weights and Measures redefined the meter in terms of the speed of light. 1 meter is now defined as the distance light travels in 1/299,792,458th of a second. The speed of light is, in the modern SI system, not measured, it is defined. It is exactly 299,792,458 meters per second by definition. If a future measurement suggests that the speed of light is different from this value, we would be forced to conclude that the meter, not the speed of light, had changed. This seems strange. Why would we define our unit of length in terms of the speed of light? Because light speed is the most stable, reproducible, universal physical constant we know. It is the same everywhere in the universe. It is the same at all times. It is the same regardless of who measures it. No material standard, not the platinum iridium cylinder that used to define the kilogram, not any atomic clock, not any physical object, comes close to this universality. The speed of light is, in a deep sense, a property of the vacuum itself, of empty space, of the relationship between the electric and magnetic fields that propagate through it. James Clerk Maxwell, working out the equations of electromagnetism in the 1860s, discovered that his equations predicted electromagnetic waves traveling at a speed that was determined by two fundamental constants of electromagnetism: the permittivity of free space and the permeability of free space. The speed he calculated from these constants matched the measured speed of light. He realized immediately that light was an electromagnetic wave. The deeper question is, what determines the permittivity and permeability of free space? Why do these constants have the values they have? This is a question for a theory of quantum gravity, or for a theory of everything that we do not yet have. The speed of light in current physics is a fundamental constant in the way that Planck's constant and the gravitational constant are fundamental constants. It is measured, it is consistent, and it is not yet derived from any deeper principle. Some physicists have speculated whether the constants of nature, including the speed of light, could have been different. Whether in other universes with different histories or different physical laws, a different speed of light might obtain. This touches on anthropic reasoning and the landscape of string theory, regions of physics where empirical grounding becomes tenuous. What we can say is that the speed of light we have is the speed of light this universe chose, and it has the value it has, and it sets the terms of our imprisonment. There is an argument developed by the physicist Brandon Carter in 1974 under the label of the anthropic principle, that the constants of nature have the values they have, at least in part, because only a universe with these values could produce observers capable of asking the question. A universe with a different speed of light, a different Planck constant, a different gravitational constant would develop differently, perhaps without stars, without heavy elements, without planets, without life, without minds. This is a contested and philosophically fraught area. It does not tell us why our particular constants have their values. It only tells us that we should not be surprised to find ourselves in a universe with constants compatible with our existence. But it raises a disquieting possibility that the speed limit we find so constraining might be precisely as large as it needs to be to allow a universe in which beings capable of finding it constraining can exist. If that were true, if the speed of light could not be different without preventing our existence, then the faster-than-light problem would have a different character. It would not be a barrier to be engineered around. It would be a fundamental feature of the conditions that produced us. Whether this is true is not known. The anthropic argument for the specific value of c is not as compelling as the anthropic arguments for some other constants, like the cosmological constant. There is no obvious reason why a faster speed of light would make biological life impossible. Probably. But the question is worth holding. The universe is the way it is. We are what the universe produced under the conditions the universe imposed. And the conditions include a speed limit that makes the cosmos effectively inaccessible on any time scale our institutions can plan for to the biology and technology we currently have. The question is whether we are actually constrained by that speed limit, or whether we are constrained by our current understanding of it. 1,000 years ago, a human being standing on the coast of Western Europe looking west across the Atlantic Ocean, was facing a barrier as absolute as the speed of light appears to us. There was simply no way to cross that water. The technology did not exist. The knowledge did not exist. The navigation techniques did not exist. The ships did not exist. And beyond the technological barrier was a conceptual one. Most people did not know there was anything to cross toward. The other side of the ocean was not a place with a name and a location. It was a void. 500 years later, in the span of a single culture, a single tradition of learning that passed from scholar to scholar, from navigator to navigator, the entire world had been circumnavigated. Every coastline had been mapped. Every major landmass had been found, named, and incorporated into the world picture of European civilization. The uncrossable barrier had been crossed. The nothing beyond the horizon had turned out to be most of the world. We are standing today in the equivalent position with respect to the galaxy. Beyond the light speed barrier is not nothing. It is most of the universe. 2 trillion galaxies. More stars than grains of sand on every beach on Earth. More planets, more possible biospheres, more possible minds, more possible histories than any human civilization could catalog in a billion years. The people who will first step beyond the light speed barrier, if they exist, will not be us. They will be separated from us by time in the same way that we are separated from the people who first crossed the Atlantic. They will have knowledge we cannot imagine. They will take for granted things we consider miraculous. They will look back on our era, the era when we first proved entanglement was real, when we first simulated wormhole physics on a quantum computer, when we first wrote down the equations for a warp drive, the way we look back on the first rough maps of the Atlantic coast, as the beginning, as the essential, difficult, imperfect beginning. We are making the first rough maps. We do not know the shape of what lies on the other side of the light speed barrier. We do not know whether warp drives are the right technology, or wormholes, or something we have not imagined. We do not know whether it will take 100 years, or 1,000 or 10,000. We do not know whether any civilization in the history of the universe has ever successfully made the crossing. But we know that the equations permit the attempt. We know that the universe has not closed the door. Can we go there?